Have you ever wondered what the future of computing looks like? Forget everything you know about silicon chips and binary code. The next great leap forward isn't just about making things smaller or faster, it's about fundamentally changing the way we process information. And the key to this revolution is something you see every day, but in a form you've never imagined. Light. Quantum light. For decades, Moore's law has been the guiding principle of the tech world, predicting that the number of transistors on a microchip would double about every 2 years. This has given us the incredible devices we rely on daily. But we're hitting a wall. Transistors are becoming so small that the strange rules of quantum mechanics are starting to interfere with their operation. Instead of fighting these quantum effects, what if we embraced them? What if we could use the fundamental properties of light itself to compute? This is the promise of photonic quantum computing. It's a field that sounds like science fiction, but it's happening right now in labs around the world, and it's poised to change everything. So, what exactly is quantum light? When we think of light, we usually picture a continuous wave, but at the smallest scales, light is made up of individual particles called photons. Quantum light deals with manipulating these individual photons, or specific collections of them, to carry and process information. Unlike classical computers that use bits, ones and zeros, quantum computers use qubits. A qubit can be a 1, a 0, or both at the same time, thanks to a property called superposition. This ability to exist in multiple states at once is what gives quantum computers their incredible potential power. By using photons as qubits, we open up a whole new world of possibilities. One of the most significant advantages is speed. Photons travel at, well, the speed of light, which is the ultimate speed limit in the universe. This means that calculations can happen almost instantaneously, but it's not just about raw speed, it's about a different kind of processing. Let's talk about security first. In our digital age, securing our data is more important than ever. Current encryption methods rely on mathematical problems that are too difficult for classical computers to solve in a reasonable amount of time. But for a powerful quantum computer, many of these problems could be child's play. This is where quantum light shines, quite literally. Quantum communication uses the principles of quantum mechanics to create unhackable communication channels. If an eavesdropper tries to intercept a message encoded in quantum light, the very act of observing the photons changes their state. This disturbance is immediately detectable, alerting the sender and receiver that their communication has been compromised. It's like having a built-in alarm system for your data. This technology, known as quantum key distribution or QKD, is already being tested and implemented, promising a new era of ultra-secure data transmission for governments, financial institutions, and eventually all of us. Now, let's look at efficiency. Our current data centers and supercomputers are power-hungry beasts. They consume enormous amounts of electricity and generate a tremendous amount of heat, requiring massive cooling systems. This is not sustainable. Photonic quantum computers offer a brilliant solution. Because photons have very little interaction with their environment compared to electrons, they generate significantly less heat. This means photonic systems can operate at room temperature. You don't need the complex, supercooled cryogenic refrigerators that many other types of quantum computers require. This drastically reduces the energy consumption and the physical footprint of the hardware, making high-performance computing more sustainable and accessible. Imagine a future where a supercomputer's power fits on a desktop without needing an industrial cooling plant to run it. But the innovation doesn't stop there. Scientists are getting incredibly creative with how they use photons. One of the most exciting areas is called structured light. Think of a standard beam of light as a smooth, simple stream. Structured light is like sculpting that stream into complex shapes and patterns, twisting it into spirals or arranging it in intricate arrays. By doing this, each individual photon can carry much more information than just a simple 1 or 0. It can carry information in its shape, its path, or its orbital angular momentum. This is like upgrading from a single-lane road to a multi-lane superhighway for data. It dramatically increases the information density, allowing us to transmit and process vastly more data with the same number of photons. This could supercharge everything from telecommunications to medical imaging. Of course, building a full-scale universal quantum computer is an immense challenge. One of the biggest hurdles is scalability. How do we go from a few dozen qubits to the millions that would be needed for truly transformative applications? This is another area where photonic systems show great promise. Photons are relatively easy to generate and control using existing technologies from the telecommunications industry, like lasers and fiber optics. Researchers are developing integrated photonic circuits, essentially computer chips for light that can route and manipulate single photons with incredible precision. These chips can be manufactured using similar techniques to traditional silicon chips, which opens the door to mass production and creating large, interconnected networks of quantum processors. The technology is modular, meaning we can build larger systems by linking smaller components together, offering a clear path towards scalable, powerful quantum computers. The applications of this technology are mind-boggling and extend far beyond just faster computers. Think about drug discovery and materials science. Simulating complex molecules is incredibly difficult for classical computers, but it's a natural fit for quantum computers. By using engineered quantum light to model molecular interactions, we could design new medicines and materials with unprecedented speed and accuracy. What about artificial intelligence? Quantum machine learning algorithms could analyze complex datasets in ways we can't even imagine yet, leading to breakthroughs in fields like finance, logistics, and climate modeling. And let's not forget about sensors. Quantum sensors that use light can achieve astounding levels of precision, able to detect the tiniest changes in gravitational fields or magnetic fields. This could revolutionize navigation systems, making them independent of GPS, or create new medical diagnostic tools that can detect diseases at their earliest stages. Perhaps the most revolutionary aspect of this research is its potential to democratize quantum technology. While early quantum computers are massive, expensive machines hidden away in specialized labs, the push towards simpler optical setups could change everything. Imagine a future where photonic quantum processors are integrated into our phones, our cars, and our home devices. Researchers are working on simplifying the experimental setups, moving away from large, complex optical tables covered in mirrors and lenses towards compact, robust, and user-friendly devices. This simplification is key to bringing quantum computing out of the lab and into the real world. It would lower the barrier to entry for researchers, startups, and innovators, sparking a wave of creativity and development that we can only begin to predict. We are standing at the dawn of a new computational era. Just as the invention of the transistor transformed the 20th century, the harnessing of quantum light is set to redefine the 21st. It's a journey filled with immense challenges, but the potential rewards are even greater. We're not just building faster computers, we're building a new tool to understand the universe itself. The future of computing isn't just bright, it's made of light, quantum light, and it's going to change our world in ways we're just beginning to comprehend. Thanks for watching. If you're as excited about the future of technology as I am, make sure to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next deep dive into the science that's shaping our tomorrow. See you next time.